Hi, good evening, everyone. Um, I hope audio is working. If somebody can confirm that in chat, that'd be nice. Okay, great. Hey, hi, by the way. So, what I wanted to do tonight is basically try to implement USB sound card using the iCEbreaker-bitsy. So let me switch. So wait, I actually have that's Bitsy, and I'm in manual focus mode, so I need to yeah. So that's a Bitsy, designed by Peter, and Jordi did the layout. That's not the latest version, but it's pretty much identical to the final version. I just have programming pads on the back instead of on the side or something. Anyway, and so I want to turn that into a sound card that actually appears as a sound card to the PC using USB audio class. So what I did is I actually I wired it up to the audio P mod that Peter. Oh, wait a second. I actually forgot to turn on the lamp here. Okay, never mind. I connected it to the audio P mod that has been designed by Peter as well on stream. Actually, it's the P mod to connect both like gamepads, and it has a stereo output audio. In theory, it's a P mod, and well, because the Bitsy to P mod adapter isn't ready yet, I just wired it up with a couple of wires, just soldered on at the moment. And the other thing I have wired is this. That's just a USB to UART adapter, which I'm going to be using for as a debug console. Because when you're trying to implement, although you can implement like a USB UART on the Bitsy itself, but when you're trying to debug USB, sending your debug message through USB is usually a bad idea. And so for debugging, I will be using like an external UART that we can just remove afterwards. Okay, I'm just gonna restore the focus here. Okay, so this I did very little preparation for the stream, kind of on purpose, because I wanted to basically do a maximum on stuff on stream live. I did do some prep. Well, I soldered the wire and stuff like that because watching me solder a couple of wires doesn't matter. And I also read the USB audio class specifications. And to create the descriptors, what I prepared is just translating the descriptors into like a C struct, basically. And so if you go to GitHub, let me know. Actually, no. I think it's no to USB. So that's the USB core that we're going to be using, which is the core that I wrote. And so what I did is I wrote that header file, which is basically the various structures that I used and some constant that I just transcribed from the specification. Let me actually load the specification here because we're gonna need them definitely. Yeah. I'm not sure what PDF viewer I actually have on this machine. But if I do, I'm just gonna load them in Firefox. It's gonna be easier. Okay, so that's the USB device class specification, which tell you how to implement all of that. So that's like 130 page, and you know, there's a bunch of structure defined and stuff like that. That's the USB specification themselves. We're gonna need this at one point or another probably. And I also loaded this, which is like just an example for another microcontroller or something. But something interesting is that they had like a summary of a USB descriptor, kind of pre-written, so that I could I don't have to start from scratch, or I have a vague idea of what I'm doing. Hey, hi Matthew. Hi Derek. Could this easily be changed for audio input, or is that something very different? No, it could actually be changed easily for audio inputs. I mean, you'd need a different PMOD, right? Because the PMOD is wired for output only. If you wanted to do input, you'd actually need an ADC, which I didn't have anything that could be used to capture analog audio. So implementing like a sound card, like an output, would be easier here. But implementing an input, you're going to see in the descriptor. Actually, this actually implements an input, but we're going to implement an output. It just instead of out endpoint, you implement an in endpoint, and that's pretty much it. Like most of it is going to be applicable. It's actually slightly easier to implement an input than an output. That's actually something we'll see, because you have when you're implementing the output, you're not like the data at which you're consuming the data is not necessarily synchronized to the USB clock, and there's a slight difference, and so there needs to be some clock synchronization issues. Oh yeah, sure. If you want to add it, I'll push that on GitHub, and then you can have at it. And if you need any help, feel free to ping me on Discord then. So that's pretty much what we're gonna do tonight. What we're gonna start with though is the hardware itself, like the actual HDL. And we're gonna start with. We're not gonna start from scratch. We're gonna start with in my repo. I have a small demo of just a RISC-V and a USB core that just enumerates. It doesn't really do anything much else, but it has the basic structure that you want. And so we're going to start from there. So let me just clone that. FPGA stream. So let's just actually build it and load it on the bitsy just to see what it does. So I'm just gonna plug the bitsy onto the PC. So if I'm first gonna plug USB converter. Yeah, that's the USB converter. And then I'm gonna plug the bitsy while holding the button so that it starts in bootloader mode, because I have no idea what's loaded on it at the moment. What did I do? Wait, I screwed up something. Huh. Just a second. It's not. Yeah, the activity is my remarkable, which is disconnecting. But I'm not sure why that bitsy is not starting up. What's going on? What the hell? I used it yesterday. What the hell did I do? Okay, so that works. Okay, I think the cable was just not correctly plugged anymore. So let me plug this. Okay, so now we have the bitsy detected. The bootloader is detected here. Yeah, no, I think the cable, because I kind of taped all the cables that come out of it together. I think it pulled out the USB-C cable ever so slightly, and so it wasn't loading it. Yeah, there we go. So now I have the bitsy detected, and I have the USB converter detected, TTY USB 0. So I'm gonna try to start Minicom on that. That's strange. I should have a console. I am in the dial group. Oh yeah, no. Okay. How do you set up things in this already? I need to disable the hardware flow control thing. Where is that? Capture on off. It's not P. It's for some reason it's not in COM parameters. Oh, it's in O, I think. Serial port setup. Hardware flow control. No. Yeah. Okay. So now I have my console. So I know the serial cable works because I can talk to the bootloader. And now I'm just gonna build this project. I need. So to build that project, you obviously need the open source toolchain, which I have installed in Open FPGA. And you need a risk toolchain, which apparently I already have. So perfect. So now I should be able to just tape. I want to build it for the bitsy, so I'm just gonna set the board environment variable to board bitsy v1, and that will select the good. Like if you look in data, you have several boards supported. You have the iCEbreaker, then you have the version 0 bitsy, which almost nobody has, and you have the version 1 bitsy. And you can either set the environment variable, or you can also do make board equal bitsy v1 depending on what you prefer. But since I'm going to be building a lot of things tonight, I just set the environment and forget about it. and then hopefully type make, and I should, yeah, of course, because I forgot that now I have forgot to do a recursive clone, because now I'm using submodules, and so I need to clone a bunch of stuff. Git submodule init, get submodule. Previously, everything was in the iCE40 playground, but I split a bunch of cores into their own repository and the build system so that you can easily reuse them. And I will be splitting off more stuff as time goes on to allow other people to reuse more easily without having to clone the entire repository of example, basically. Okay, so now I can do make. That should build everything. Yeah, I mean, so the USB core I implemented was basically what I wanted is I wanted it to be small, basically the core itself, and be completely independent on the number of endpoints or the configuration of endpoints that I wanted to use, because some of the stuff that I wanted to use it is to create, like, well, you can't create 20, but you can create like 16 or 15 UARTs, something like that. And the way the um, the whole RTL implementation was written in the original code from Luc Valenti, the more endpoint you have, the more resources it uses, which is something I didn't want. I wanted to be able to dynamically reconfigure and have an application that has different USB configuration with different endpoints and stuff like that, all completely dynamically, and with a small hardware footprint. Like the USB core itself takes about 600 LUTs, logic cells. You do need a soft core, sorry, which at the moment I'm using a RISC-V, but I've also been working in parallel to have my own soft core, which is much smaller and would be targeted just as being a USB controller, basically. So yeah, that was the general idea, because I mean, some things, like if you want to implement a lot of control requests and stuff like that, you're gonna have a hard time in RTL, because that's progressively gonna grow your number of logic of state machine. That's gonna impact your Fmax and stuff like that, and that's gonna be kind of annoying. Here, the core is done. It supports everything. It is not completely reconfigurable, but if you want to do some weird stuff, you can actually play with USB. Like if you wanted to fuzz USB or do some weird stuff, you can actually do that too, because the if you look here, if you look in the core itself, NO2 USB, like the transaction layer is actually implemented using a microcode, and so you have like a very simple assembler, and here you have the microcode that runs the state machine of the HDL code, and decides what to do depending on the types of packet it does. And so if you wanted to modify that kind of stuff, you can actually do it if you want to. Yes, it can be anything. Basically, you have all 32 endpoints, and you can configure them however you'd like. If you we're gonna look at this later, but if you look here, I don't know if it's in architecture. No, that's how the code is organized. But here you have the register memory map, and for each endpoint, you configure what type of endpoint it is. If it doesn't exist, if it's an isochronous endpoint, if it's interrupt endpoint, bulk or control endpoint, that kind of stuff. And you have like an interface that's fairly similar to what you find in microcontroller, where with you have if you look in the architecture, you have 2K of transmit buffer, 2K of receive buffer, and you allocate buffers for packets however you'd like in those. And endpoints can support either simple buffering if you want to spare memory, or and they're not very high performance, like a small interrupt endpoint. Or in the case, what we're going to do today is we're actually going to implement a dual buffer mechanism for the isochronous endpoint, so that we can sustain the data rate and be sure not to miss packets and that kind of stuff. Wait, so it actually built, so I'm just gonna do, so the bitsy is programmed via DFU, so I'm just gonna do make DFU prog, which is gonna it's like make prog for the icebreaker, except here this will call DFU util. And of course I don't have the rights to access that device. Oh damn it. Okay, how do you, so I need to add like a rule or UDEV rule for that, right? I never use that machine for FPGA development. Usually I use my laptop. I should have tested that before. UDEV rules, DFU. That's absolutely not what I want. That looks like what I want. etc UDEV rules.d. So the vendor ID for the bitsy is this. I'm like gonna move that in the right repository. CMP /. And then do I need to, does that work? No. Do I need to reset it maybe? Wait. Okay. Make DFU prog. Okay, so now I can load the firmware. Wait, something I'm actually gonna do is also allow the runtime PID and not just the bootloader, so I don't have to. Yeah, I did the UDEV IDM, and I thought that would take it directly, but I in the end I just unplugged it and oh, I need to do UDEV IDM reload and trigger. I just did the trigger. Okay, I should have done reload and trigger. Anyway, now it works. But thank you for the tip. So now I've loaded the bitstream. I also need to load the firmware because it's a RISC-V. The only firmware that's built into the bitstream is just the boot code. I'm going to explain like very quickly how the SoC is set up once I've loaded the initial state here. So I also have make DFU prog here. Okay, and we see here it actually booted. I mean, it's very similar because the bootloader is based on the same SoC, but instead of saying booting DFU image, it says booting app image, and so that's the default SoC. And by default, it does not actually connect to on USB. You can see here the bootloader disconnected, but nothing else connected. I have to send the C command, and then it actually enumerates. And by default, it implements, or by default, it doesn't implement. It enumerates as a USB ACM device, but there is absolutely no code to support it. So there's no. If you try to access it, it'll just do nothing. But you see here it enumerated as a ID product 6147. Okay, so I'm gonna quickly explain how the SOC is set up and how we're gonna modify it to add support for audio. So let me switch setup here. Does that work? Yeah, perfect. Let me just drink quickly. Talking all the time is harder than it looks. Yeah. So the way the SoC is set up at the moment is you have the CPU. At the moment, it's a Pico RV32. I'm looking into making it swappable for a VEX. I did some tests this afternoon, but didn't finish tonight. And we don't really need much performance anyway. The CPU is really not going to be doing much. And it connects to something that's called the bridge, which basically splits the memory space into 3 zones. There is a 1K of block RAMs. There is 64K of single port RAM. And then there is Wishbone bus on which we find UART, the RGB LED controller from the UP5K, the SPI controller from the UP5K, the odd IPs that are built into the thing. Yeah, but I've only been talking for like 20 minutes? Oh damn, 30 minutes already, and I'm already feel it in my throat. So, what else do you have? Oh well, you have the USB core, which actually has 2 kind of access ports. You have the USB data. I'm gonna call that USB buffer. So it's basically accessing the the memory buffer from the USB core, and then and the USB buffer, they also talk to the USB core itself. And then you have something that actually cross clock domain and talks to the USB core itself, because this part here runs at 48 megahertz. The rest runs at 24 megahertz, basically. The PicoRV just isn't fast enough in the UP5K to just work at 24 megahertz, at 48 megahertz. So I need 2 clock domains. So that's currently the way the SoC is set up. What we're going to add is basically just go on the bus and plug an audio peripheral that's just going to talk to the couple of pins to the PMOD. That's basically what we're going to add as a first step to get audio. So if we look in the source code, I can get both here, for instance. Let's look in the RTL source code. So that's the top level with the external pins, which there is really just the SPI, the USB, the UART, the RGB, the clock input, and a button, which is the button is then actually wired to the SoC itself. It's wired to a hardware block, which if you press it for a long time, it reboots the bootloader, basically, like so that if you screw up, you can go back to the bootloader without having to unplug the board and replug it. You can just press the button for a long time, and the hardware takes care of that. As for signals, well, you have the Wishbone bus, which is pretty classic. You have what I've called the SoC PicoRV32 base, which basically includes all of this. So that's what I call the base, because that's the memory subsystem. Really is, I mean, you need one basically, and so I just globbed everything and just made the peripheral configurable so that you can easily add or remove some peripherals. Something I didn't explain is why I have 1 kilobyte of memory separate from the rest. It's because on the UP5K, the single port RAM, the large 64K memory zone, you can't initialize it at boot. It comes up with random values, and so the 1 kilobyte of RAM can be initialized, and so it's initialized with a very small bit of code, which goes and read the SPI flash and copies 64K from the SPI flash into the SP RAM and then jumps into the SP RAM. Yeah, that's why I have 1 kilobyte of RAM isolated there, which is only used at boot and then kind of wasted afterwards. I mean, it's not wasted. I use it for the stack space, which means you only have 1K of stack space unless you move the stack pointer, but whatever. It's been enough for now. So yeah, that's the SoC base. And then you just find the peripheral, which pretty much for each peripheral you'll find the UART instantiated, the wire to the outside pins, and then connected to the Wishbone bus. The Wishbone bus is actually pre-split into like one bus per peripheral. So the cycle, ACK, and read data signal, which are the signals that are not common between all the peripherals, are kind of pre-split for you, so that you can easily wire it without needing any address decoding logic. Basically, it's all of that is handled for you. Same thing for the SPI core. I wrapped the IP from Lattice into something that neatly appears as a Wishbone bus that you can wire directly. Same thing for the RGB LED, and same thing for USB. Actually, this part here is what I named SOC USB, which is all that you need to just have USB basically. And then warm boot and this thing here, that's the stuff that handles the fact that if you press for a long time on the button, it will reboot to the bootloader directly. And the rest is setting up the clocks and because the clocks are set up by a PLL and the PLL is not simulated by iVerilog or whatever simulation tool you use. If I'm in simulation, instead I replace them with hard-coded simulation clock basically. So that's pretty much all of there. And I mean, all of those peripheral, like the UART or the iCE40 Wishbone, stuff like that, you can actually find them if you look in that repo. So the two hardware IP are specific to the iCE40, so they're in the NO2 iCE40, Nitro iCE40 FPGA, and you'll find the SPI Wishbone wrapper, the iCE40 Wishbone wrapper, and the RGB Wishbone wrapper. And if you look, you even have documentation for them with the address map, although for most of them, because they're just wrapper for the hardware IP, they just tell you basically which tech thing you need to look at and how it's mapped to Wishbone, but there's not much else to say. If you look for the UART is generic, it's not specific to the iCE40, so it's in the Nitro MISC. And here you find the Wishbone UART, and there might actually even be documentation for it. Yeah. So you have the registers are documented here if you want to control it yourself, that kind of stuff. Yes, the bootloader that's currently in the iCEbreaker-bitsy is the NO2 bootloader, which is has been split off recently from my iCE40 playground. I put it in a separate repository so that it can be more easily ported to other boards. As I said, currently it's specific to the iCE40, but it's possible to adapt it for ECP5 because I mean I've done it for the Academy badge. I have not finished porting all the modification needed, but I definitely intend for that particular repository to support other variant of the iCE40. So not only the UP5K, but I want to get it running on the tiny FPGA BX. The main issue to porting it to that is the fact that there is no single port RAM. I don't have like a large 64K array of a single port RAM on there, so I need to reduce. I need to change the architecture and just use block RAMs for that. But there's enough block RAM; it's not a problem. And I want to port it to the ECP5 also because I have all the cores that are needed to port it. Like I have a SPI instead of using the UP5K. I'll do SPI core. Well, actually, I did that after the lockdown, but no. Here in Belgium, we're actually pretty much entering a second lockdown, so I'm gonna have more free time. But yeah, I'm trying to advance and help people reuse that stuff if they want to, if they're interested in reusing it. Okay, so the hardware. Because yeah, we're 45 minutes and I haven't actually implemented anything yet. Let's go to this. So we want to play sound. So the way this is gonna work, I haven't implemented it yet, but I obviously thought about it, and so I know pretty much what I want to do. The sound card is only going to support one sample rate, 48 kilohertz, because I don't know, it seems like a nice number, and with a 48 and 24 megahertz clock, that seems like a good choice. I mean, I could do 96, right? But I have a one pin to output audio, so at some point it doesn't matter. Yeah, and it's gonna be 16-bit samples. Honestly, I'm not necessarily sure. I'm definitely not gonna have 16 effective bits like in the end, but it's either 8 or 16, and I think 8 is not enough because you really need to be right in the exact dynamic range of your 8 bits if you want it to sound at vaguely good. So I'm just going to use 16-bit samples from the host. So this is going to be 4 bytes per sample. We get 48 samples nominal by USB frame, which means we get 192 bytes per USB frames. That's okay. That's going to be our data rate, and that, I mean, we can go up to 512 bytes per USB frame, even in USB full speed. So we don't have any problem here. Yeah, I definitely don't want to do 44-100. Definitely not. So the way this is gonna work. So that's stereo. Yeah, I forgot to say, but it's stereo, right? Because why not? We're gonna have 2 PDM cores, pulse density modulation. They're gonna be first order because honestly, I already have some, and I don't want to spend my. Have you benchmarked the bandwidth of the USB sock? Yes. 12. Like I can saturate the bus basically, especially with isochronous data. With bulk endpoints, it's a little harder because bulk endpoints have a maximum packet size of 64 bytes, which means the CPU has more work to do, right? Because it moves relatively small amount of data. But with isochronous, you can move 512 byte packets, which means the CPU core really doesn't have that much to do. And I have an application where I've actually used without any issue up to 8 megabits of the bandwidth because I have 2 E1, the old E1 telecommunication interface, which is 2 megabits, and it's transmit and receive. So each port is 4 megabits of data transfer, and I have 2 ports at once, so I have 8 megabits, and I have no problem transferring that. Yeah. So I'm gonna have my 2 PDM cores. I want volume and mute control. So I'm gonna have volume and mute. Using the iCE40 DSP. We're gonna try DSP inference from USS because I never did, and I'm wondering if it's gonna work at all. We'll see. We obviously need a FIFO. No, I'm gonna draw it as one single FIFO because it's going to be entirely synchronized, right? It's not two independent FIFO. They can't have different levels. It's just one big FIFO. So our large is going to be that FIFO. I think I want it to be probably at least 5 milliseconds of audio. Let's see. I just want to see how much block RAM that's going to take. Oh, you can't see that. No. So 5 minutes, 48 kilohertz audio, 4 byte per sample, 5 milliseconds of audio. And well, actually, it's not 4 bytes, it's 32 bits. I want it in bits. So that's going to be 7,680 bits. That sounds low. Did I screw up something here? 32 bits per sample. 48,000 samples per second. Okay, so that's actually very low. So I don't have to worry too much. I can probably buffer. I can probably have a FIFO that can hold about 10 milliseconds, and we're gonna try to maintain its level at around 5 milliseconds, so that we can absorb some USB host, rate variation, either too much or too little. And so we need that many bits, and that many bits is, well, basically we need 4 block RAMs. 4 block RAMs, I'm good with that. So yeah, we're gonna have a FIFO that's about 10 milliseconds. We're gonna have a level counter. So I have a FIFO core that I can reuse that's configurable and stuff like that, but it doesn't tell me how much data is in the FIFO. And although I could modify the core to output that, it's pretty much as easy or as hard, or at least as costly in hardware, to just do an external level counter, because that FIFO is synchronous. Like everything here is clocked at 24 megahertz, right? So it doesn't matter. And then we're gonna have a tick counter, which generates a tick every 500 clock cycles, right? 24 megahertz, 48 kilohertz, 500. That's gonna clock enable everything. And then we have our Wishbone interface. And then I'm just thinking what we need. What else do we need? I mean, we obviously need like a FSM that's gonna control some stuff, because when the stream is gonna start, you don't want the hardware to start pulling samples directly. Basically, you want to wait, like 4 or 5 frames of you get 4 or 5 frames of data from the host to fill up your FIFO, and then once your FIFO is actually filled in to like mid-level, then you actually start playing audio, because if you start directly, you're just gonna underflow directly, basically, which is not what you want to do. Yeah. And the other thing we're gonna want is tick per USB frame. So that's something I encountered previously when implementing another USB peripheral. Is nominally there is 192. There is 48 samples per millisecond, and one USB frame is 1 millisecond. But of course, like your 24 megahertz is not exactly the USB 48 megahertz. Like when your 48 megahertz, is not exactly the USB 48 megahertz, which means the clock drift eventually. And so the way synchronization works We can actually look at the specification here. It's actually somewhere there's something called synchronization. Special consideration for isochronous transfer, clock synchronization. There you go. So basically, here they explain to you that you've got a problem because stuff is not synchronized, right? And so you can have different types of devices. Oh, and like audio, just and you can have different types of synchronization type. You have asynchronous, synchronous, and adaptive. So synchronous is you basically use the USB start of frame as your clock base. Basically, that's how you synchronize, and therefore you're always perfectly synchronized because you use it. There's adaptive, which is more like a PLL thing, if I remember correctly. Yeah, well, you're not using the start of frame. Sorry, you're using literally the rate at which you're receiving data to know at which rate you must consume data. And we are going to be in the asynchronous case, which is we have our sampling frequency is completely independent from the USB frequency rate. But then what we must do is provide explicit feedback. And so we have an isochronous endpoint from the PC to the device that sends audio data, right? And then we actually also have an isochronous endpoint from the device back to the PC that tells it for every frame how many samples it consumed, basically, so that the PC can dynamically adapt the data rate to the data, actual rate, basically. And that's what we're going to use here is an explicit feedback endpoint, because I think that's going to be the easiest to implement. Whether or not this is going to work, because I honestly have no idea if like Linux audio actually implements that correctly or something, because it's not. I don't think it's very often used. Most of the USB card I've seen are actually adaptive, or at least they declare themselves as being adaptive. We'll see if that works at all or not. Yeah. So let's go back to the hardware. So I think that's pretty much all we need, actually. And so our Wishbone interface is actually very simple in a sense, because we need to be able to write samples, which are going to be 32 bits, to the FIFO. We need to be able to write the volumes, which are going to be 32 bits, 2 times 16-bit multiplier. And that's pretty much. Oh no, we need to be able to write some control. In the control, we have the mute, and we have the run status to tell the logic to actually start, basically. I think that's pretty much it. And as far as read is concerned, we need to be able to read the FIFO level. We need to be able to read the current status, and we need to be able to read the tick counter. And I think everything is going to fit in like one single 32-bit static word. I don't think we really need several read registers. Yeah, I think that's gonna be fine. So I'm gonna say the status is address 0. The right of control is gonna be address 0 as well. And volume is gonna be address 1, and samples is gonna be address 2. There you go. That's our memory map. We only need 2 address bits. It's like trivial hardware. Yeah, you can split. You can split the registers, but it tends to generate more logic, and so I usually write things for minimal logic size and putting more burden on the software. I mean, one of the counter, like this stick counter, is going to be 16 bits, so I'm going to make sure it's aligned. That level counter is going to be probably yeah, exactly, yeah. So yeah, let's start creating hardware, shall we? I need to switch the scene here. I'm actually gonna create a new. Okay. Data FPGA stream. I'm just. No, you know what? I'm just gonna create a new project. I'm just gonna copy the current one. I'm just copy everything. Because if I want to push the result and have it available as a separate example, I don't want it to mix with the minimal code. At some point, I will have to make some parts common and stuff like that to be cleaner. But for the sake of this stream, I'm just gonna copy the entire thing. I'm gonna call that USB audio. That's pretty much the only place where the this appears. And the other thing I'm gonna do is change the string. So you can change the descriptors. They can be specific per board, which means that I need to actually write them several times. And there you go. Okay, so let's just create new hardware. Usually I just cut and paste because it's easier. I don't actually need configuration for this. We're gonna have I need to yeah. Okay, so that's what the interface is gonna look like to the top level. So I'm just gonna integrate it right now, even if currently it doesn't do anything, obviously. Vim top.v. So I'm gonna plug it. So currently you see USB is peripheral 4 and 5. One is for the data buffers and the other is for the control register. So USB actually uses two places on the Wishbone bus. Audio is only gonna use one. Actually, actually I can, yeah, all of that is the same. I can just copy here, and audio is just gonna connect to audio external pins, right? So here, so now I actually need to extend the Wishbone bus because I have 7 peripherals on the bus. So here I can declare how many peripherals I have on the bus so that it only creates the decoding logic for that many peripherals. So I just bumped it by 1 so that I have a peripheral number 6. It starts at 0, obviously. And then I need to add an audio output. So I instantiated my peripherals, connected it to the Wishbone bus, and I haven't actually connected it correctly because I only have 2 address bits and I am on peripheral number 6. No, I need to top bitsy v1. I need to declare the pins. Where did I connect my audio P mode? That's a good question. I have no idea. Let me look that up. And see, that's why it's useful to have the actual pins on the seal screen. 36 and 43. 36, 43. There you go. If I so currently I have nothing implemented, right? But if I do WC AQR, so that acknowledge all the Wishbone requests without doing anything. Data 32H. Okay, that's like the minimal peripheral that will just not crash the bus, basically. But that should build. So I'm just gonna check that it actually does. And it does build. Yeah, I'm scrolling, but yeah, I think yeah, but that was like a note for Peter, because on the version of the bitsy that he sells, he basically numbered the pins on the sales screen are numbered, 1, 2, 3, 4, 5, 6 in the order of uh, the tiny board it's based on, basically, but they're not the FPGA pin numbers. And so you can look up the pins on the cell screen to know, okay, yeah, it's a tiny, it's like feather pin 3, but then you actually need to look up, okay, feather pin 3 is actually FPGA pin 32. And on the board that I manufactured, I actually replaced that. I replaced the cell screen and put the actual FPGA pin numbers. You are building risk use. Oh, well, yeah. Thank you, Conrad. That's a good point. I've tested absolutely nothing. Ah, yeah. That doesn't work as well. So what did I screw up? 201. I always screw up something stupid, right? But oh, yeah. Do you see another one? Yeah. Good catch. Oh, yeah. And of course, the other thing that I forget is I forget to add it to the makefile. Like in the makefile, you have the source of the project, but you need to actually tell it which file to compile, right? So I need to add it there. Huh. That's interesting. Let me. Yeah. Okay. Obviously, the makefile has kind of a small problem. It does not recreate the Yosis build script when the makefile is modified. So that's something I should change. So the other thing I want to check is if the resource usage, okay, the resource usage is more or less what I expect. Like it's slightly less than 50%, because if you screwed up something and you end up with 1% of the FPGA used, then most likely you screwed up something. But this seems perfectly plausible. I can actually try to just program it. So I can do make DFU prog. So something that's nice about this, the base SoC that's here, is that it actually implements DFU runtime. So if you do like it's not in the bootloader, right? It's currently running the application image, but the application image is DFU aware. It's not the boot. It doesn't have the bootloader code, but it's aware that it supports DFU, and it has the capability to receive a command that will reboot into bootloader mode. And so you can do make DFU prog. The bitsy will automatically reboot in the bootloader, flash the board, and so if I do that, yeah, you see, it automatically rebooted into the DFU image, downloads the new bitstream, and well, by default it doesn't reboot into user mode, but you can just do DFU -e A0, and the DFU bootloader exited and restarted the app image. Yeah, I mean DFU I think is a good mechanism that works pretty well in my opinion. And yeah, it's nice that they thought of that you can have a runtime mode, which is very minimalistic. Like the only thing you have a small blurb of data in the descriptors, which costs you almost nothing. And then you need to handle one single DFU control request, which is reboot to bootloader, basically. Um, okay, so that's the base thing. Now we can actually implement our audio. So so in the blocks that I know I'm gonna need is I know I'm gonna need some pulse density modulation, and I know I'm gonna need a FIFO. These are both blocks that they're utility blocks, so I've already implemented them at some point. Did it enumerate with the new descriptor? That's a good question. Oh wait, I need it. No, it didn't, Matthew, because I only flashed the bit stream, the FPGA bit stream. I didn't flash the new RISC-V firmware, and the firmware is what contains the descriptor, right? But like, let me actually modify the firmware. So what I'm gonna change is, here it's waiting for a command before calling USB connect. I'm just gonna make it connect directly. So here, directly connect. The firmware, when it boots, directly enumerates. And I can change the boot app image to boot audio image, for instance. And here I can make DFU prog as well. Reboots to bootloader, flash and reboot. And now it says boot audio image. And if we look at enumeration, iCEbreaker-bitsy audio demo. So the hardware. Let me go and grab this. So most utility cores that I use end up in NO2 MISC. That's when it's not worth a repository by its own. And here you will find a PDM core, pulse density modulation. So I'm just gonna take this here. And then I'm gonna need a FIFO. And I have a FIFO here, yeah. Synchronous FIFO implemented using block RAMs. Super simple thing. Here, boom. So let's see. So we want a 32-bit wide FIFO because 16-bit stereo. And we wanted 10 milliseconds, which is 48 samples per USB frame, 10 foreign, so basically 512 depth. I kind of like, I mean, it's, everybody has its own HDL style. I kind of like declaring my wires kind of in advance and at the top, so that I know kind of all the wires in my design and see how they're going to be connected to each other. It helps me mostly when I need to reread my code later on. FIFO write, FW. I'm also getting used to that keyboard. I'm very used to my laptop keyboard, but I haven't much practice, in recent years with like a full side, full travel keyboard, and so I tend to not be as fast as I would normally be. So yeah, the wires, okay. Now between the FIFO and yeah. I know, like wiring things and formatting stuff and stuff like that. It does take some time. Um, Usually, it doesn't bother me too much because um, I think about about the hardware I'm building while I do that, right? I can do that at the same time. So the time it takes me to type and stuff like that isn't too much of an issue. But yeah, I'm. I mean, I know there are, better Vim user out there that could do that much faster and things like that and use more automation, stuff like that. But I tend to forget how they work. Yeah, I'm not a big fan of my gen. Just honestly, just the fact that I just I absolutely can't stand the fact that my gen works like that. No, sorry, works like that. Sorry, that's not a bit notation. That's wrong. Correct is this. And I really can't stand that. And because I mean, in MyGen, you still need to wire stuff up. You still need to wire the signals. You still need to do everything you normally doing. Like it doesn't do anything for you. Sure, I mean, like you have a FIFO already implemented in MyGen. Well, I already have one implemented here. Like I didn't have to implement it. It was already done. Like I reuse my code. I tend not to reuse other people's Verilog code because I don't necessarily trust it. But then I don't necessarily trust NMyGen's library code either. So I would be re-implementing a FIFO in NMyGen. So that doesn't really help, right? So yeah. Pulse density modulation. No, I want 16 bits. I do want dithering. And because we're on iCE40 and it exists, I'm going to use the iCE40 5 variant of the PDM core. And I want an array of instance for this. So that's the audio output, the PDM output, which in our case is the audio pins. That's the output enable, which we're always going to enable. That's the clock, which is our system clock, which is, yeah, RST. And the that's going to be audio. How am I going to name that? Naming stuff is always the hard part, right? It's the value that's going to be output. So I'm just going to call that AV out. And I'm going to make that an array of, yeah. So between the FIFO and the PDM output, we have the volume and mute control. Well, it's not control, it's just volume and mute, which we're going to need to implement. What else do we need to implement? We need state machine that's implement the control, and then we're gonna need our Wishbone interface logic. I'm just filling out what I need to implement, basically. I'll figure out what to put in those after, but no, that doesn't work for because that's an that's a Verilog array, and it doesn't automatically expand. So when you use an array like that, I mean an instance array, the signals that you connect either need to be the same width of the array, but here AV out, there's 16 bits, and so the signal that you connect must be 32 bits. It can't be an array of 2 times 16 bits. It doesn't recognize that. You need to expand it manually like that, which is a bit of a pain, honestly. But the other option is I could have made AV out like a single 32-bit signal, but let me see. Oh, damn it! Sorry, I lost the window. Okay. So volume. Oh yeah. So something I wanted to test was the implement the DSP inference basically, and does that work with? So the way the data. So what I'm gonna have is basically the sample from the FIFO that I want to multiply by the volume, and then I want to shift that by 15, I think. because the result is going to be 32 bits, but I'm going to use 0x8000 as being equal to, wait, no, because I don't think the multiplier supports a mixed. You can't have like one value signed and one value unsigned. I don't think it does that. I think the multipliers only do either everything signed or everything unsigned. So I need 0x400 to be equal to volume 1.0 or 0 dB basically. And then I'm gonna support volume minus whatever dB to 0 dB, which is basically just feeding the exact samples as is. And so I want to shift by 14. Let's see what the DSP inference does. Let's try that. I'm just gonna create a test module, input wire sample, input wire volume, input wire CLK, input wire mute, out. What? Oh, son of a bitch. Yeah, and I don't have any, man, I have no idea to, no. Oh, does that work? Okay, thank you. So I'm just gonna try synthesizing that module, just calling uses manually and see what it does. What did I call that module? DSP.v. How do you declare something signed in Verilog? I never use. You just say signed? Reg signed. Okay, yeah, that was not too complicated. Okay, so that somewhat worked. And we generated one SB Max 16. Now, what I'd like to know is, I want to generate a pipeline with, well, things are pipeline basically. So I want to register that stuff. Wait, why don't I have? What did I do that I don't have automatic indenting anymore? Set smart indent. So I'm registering the inputs. Yeah, I know I need to make those signed as well. Oh, nice. It seems to have pushed that correctly. So if I write oh yeah, I can call $sign to just force it instead of declare. Yeah, I think that's actually better because it's gonna be annoying for me to have to carry that thing and not forget it anywhere. So I much prefer to have to tell users to yeah, okay, Vim. Yeah, the Macs have 3 levels of. Actually, let's look at the SB Mac 16 documentation. So it has input registers. It has pipeline registers for the multiplier, and then you can actually pipeline the output and then directly go out. I mean, it depends how it configures it, right? Because you could actually pipeline here and then go there and then set that to 0. If you really wanted to have another level of register, but I think you can just take that one. And so you can actually have like an inside pipeline registers. I don't know if Yosis is going to support that or not, though. If I put another... Okay, so that's the output it generated, right? So it did not actually use the reg. So yeah, what it basically it used that register, I think, and that output register. So if we look at nope, you're right, Conrad, I'm an idiot. Oh, well, look at that. No, it actually uses the I registers. What a surprise. Yeah, good catch. And so what register does he use? So it uses A and B. A and B, okay. So far, I'm with you. Let me zoom on this because I'm sure you, I mean, I can barely see anything. So I'm sure you're not seeing anything. How do you zoom on this? Okay, here. Okay. it's a very bad quality scan, but whatever. So yeah, it doesn't actually tell me the name of the. Okay, where is? Okay, so it uses pipeline multrec 1, but not pipeline multrec 2. So C6 and C7. C6 and C7. C6. Okay, so it uses those. It uses these, but not C7. Okay, and what if I add another register? The thing is, here I don't care, right? I don't care about the delay of 3 clock cycle. I can register as much as I want, and I'm mostly just curious if it's gonna work or not. What? So, Conrad, what did I screw up? Because here it's not using any logic anymore, which is a bit strange. Yeah, it goes up to, but the question is why? Because I'm still like, I'm outputting something to out R, right? Oh, I know. I mean, I'm not entirely sure, honestly, why it was entirely optimized out, because there should still be something, right? Yeah, that doesn't fix it. Huh. Okay, so driver conflict for out. Driver conflict. I'm driving. What? Maybe it doesn't like the name out. Let me also. Yeah. Slash tmp dsp. That's the file I'm editing. Well, you know what? I mean, I want to move on. Like that's weird. Definitely needs investigating because I think it shouldn't do that. Yeah, I don't know either. But at least I know that I can pipeline the input and the output, and it just doesn't like the third pipelining level apparently. That might be a user's bug. Maybe I should try to update users, although that one is really only a couple of weeks old, so I don't think that's gonna fix anything. But I just want to try to advance a little. Um, yeah. Okay. So um, never mind. Oh, something I know. Something else I wanted to check quickly is does it support reset? So that worked, right? Yes. And now if I have if mute AV0 else. Ideally, I'd like it to basically wire to the reset of the output register or that one, whatever. That's what I'd like it to do. Question is it going to? No, it didn't. Shit. So instead of it can't pack the register if there is a reset. Um, can it do it for an input register? No, 0. That doesn't work either. Okay, so it can't pack resets, which is nah. Okay, so, I mean here for the sake of going fast, I'm gonna use the DSP inference, but in reality, I would probably just instantiate the primitive myself because it doesn't pack everything I want it to pack, and so yeah. Yeah, I think that's what I'm gonna do at the moment. Is implement the mute in the software, where basically I will keep the volume in a memory cell and set it to 0 or 1. But I wanted to also to be able to mute the output when the core is disabled, basically, when there is no samples or that kind of stuff, which only the hardware uh, knows about. Yeah. But yeah, at the moment, that's just um, gonna work. So I I need to do everything twice for every channel. Yeah, exactly. Or actually, no, it's not actually off because when I mute, um, the the steady level of the PDM is gonna be 50%, right? Because I need to be able to generate pulse up and down. And so the zero value is gonna be half level basically. Before the PDM, after the volume and here AV out, I'm gonna have to do basically a XOR with 0x800 just to invert the MSB. Yeah, exactly. But here, okay, I'm just gonna implement the volume and not worry too much about that because it's already been going on for 2 hours and I haven't implemented the hardware. I thought it'd be much faster than that, to be honest. So let's try to speed that up. Um, I'm just having trouble finding variable names, basically. 31, 0, and I want to shift it by 14. So here I'm basically taking the multiplier output. Yes, the audio P mode is AC coupled. Any DC value would stop producing noise, but ideally what you want to do is when you turn the volume on and off is to progressively ramp it to the mid-scale value so that you maximize your dynamic range up and down. And you want to ramp it up and down kind of progressively to avoid the click when you mute or unmute. Honestly, I'm not gonna bother doing that here just for the sake of moving on to implementing the USB side as far as possible, as quickly as possible. That's something that can be added in the gateway afterward. Basically, here I just want to get audio output. Okay, I think I didn't screw up. Just for the sake of consistency, I'm gonna call this AV volume. So that's the input register of the multiplier for the volume, the input register for the sample, and the output of the multiplier. And I need to be arrays. So I think I'm good here. That takes the output of the FIFO and pipes it to there. But really, yeah, I mean, we'll do it like that, but there might be some noise once it's not. Yeah, never mind. Okay, that's the FIFO. Uh, 512, that's A79. I want to generate a tick every 500 cycles. No. So what it does is it selects the bits starting at 16 multiplied by I, and it takes a slice of 16 bits. Yeah, exactly. It's like a shorthand, a completely unreadable shorthand if you have no idea what it does, but it's very convenient. Yeah. Okay, so that generates a tick every so often. So when do I want to pull from the FIFO? If it's not empty, and we have a tick from our time base, and our state is run. Now, of course, I need to actually define the state, but yeah, one thing at a time. Actually, if the state is run or the state is flush. So the way it's gonna go is, by default, it's in the stop state. When the host thinks that there is enough data in the FIFO, it's just gonna enable it and set it to the active state. At that point, one samples get pulled every 500 clock cycles, and when the host wants to shut down the stream, it says, okay, disable, and our state goes to flush, so that we flush the FIFO and continue playing the few hundred samples we still have in the FIFO, so that we empty it and don't keep that data for the next time we actually enable it. Read. Oh yeah, we also want a level counter. So it's a 512 FIFO. So we're gonna have a 10-bit counter. FIFO level wire. So I think that's correct. Basically, I want that to be 1 when we write to the FIFO and we don't read. And I want it to be 0 if we read and write. And I want it to be -1 if we read and don't write. And you would think that I could just put that in the as different if clause in there, but if I do that, yeah, users won't understand that it can pack this that way. by just generating two signals and then because logic packing with addition, depending on the carry rules, is very picky about what it actually packs or not. And I know it should be able to pack that. Um, um, that's why I write it that way, basically. Okay, so we have a read from FIFO that goes through the volume, that goes through the output PDM and everything. So far, so good. We have our tick. So we need our FSM. Yeah, I'm actually I think this SOC has a simulation setup, so I will definitely run like try to modify the boot script and instead write a couple of values to the core directly and simulate it for like a 1 millisecond or something just to see if it's doing anything vaguely valid before even trying to run it on hardware, because there is so much stuff in there that I have no idea if it's going to run or not, that there's no point in trying it in hardware. I want to simulate it first. I mean, we can. It's actually an interesting thing. Maybe I'm wrong, and maybe no, it packs it correctly. But let's actually test this, right? FR in a FW in a. So it's kind of a tangent, but I mean, I think it's interesting. Maybe I'm wrong, and you couldn't care less, but what the? Oh, never mind. Wire. Okay, so that took 12 LUT4. That's what I expect. Basically, 2 LUT4 to generate this, and then 10 flip-flop for the register, which is 10, right? You have 10 flip-flop and 10 LUT for the addition, and then 2 LUT to generate those two signals. Now let's try to write it the naive way. If F R in a and not F write inner. So we read, but we don't write. And if we do the opposite, if we write but don't read, we do +1. That's kind of the naive way of writing the same thing, right? Yeah, I can do that. Let me. So that's the old code, and I can do. Wait, what? No. Oh, okay. But basically, yeah, with all the carry, it's not super easy to see. But you have all the LUT4 that will perform the additions. And they all go to that signal that gets registered here, right? You've got a bunch of registers. I don't know if you have the yeah, but here you do have like the two. You see the two LUTs here that generates the two weird signal. And then that gets distributed to a bunch of signal with all the carries and the SBA-LUT4, one per bit that generates the addition, basically. Yeah, the second one is what people would normally write if you trusted the compiler. No, let's see if yeah, that's 29 LUT4. So we went from 12 to 29. That's like 2 point. That's like 100 times 120% larger or something. So yeah, that's why I write it in a weird way. I mean, I can try to show the graph of that, but honestly, the chances of me understanding what it came up with are probably nil. Like I'd have to analyze the each LUT to know what it did, and yeah, I have no idea. It came up with 29 LUTs basically, but yeah, that's why like I would love to be able to write logic the naive way and have the optimizer find the optimal solution, but yeah, that's just not the case at the moment. And no, to be clear, I'm not blaming Yosis or the open source tools, because I have to do the same kind of crap with Xilinx, Lattice. That's all of them, right? You kind of have to write your HDL in a way that they will understand what you want them to implement, and certainly not describe. You definitely don't want to describe the behavior you want, basically. No, I mean, with the only other tools I played with was Lattice and Xilinx, and not really. No, the Lattice tools tend to produce faster but bigger logic, so it optimizes more for speed. But I didn't find them that much smarter. And same for Xilinx, basically. At least a while ago. I haven't rechecked recently if it has really gotten better. But that's mostly because, like on the iCE40, it's a very small FPGA, right? Which means that if I start wasting, 14 LUTs there, 15 LUTs there, and that kind of stuff, I mean, I only have 5,000 total, so I have to be much more careful on the iCE40 that I have to be on a ultra scale Xilinx, which has thousands and hundreds of thousands of LUTs, right? One thing I will say is that the inspection, like the Yosis show command, and especially with all the filters you can apply and stuff like that, it's much easier to inspect and see what actually got implemented. I mean, I could run like a small module through it easily and inspect it and that kind of stuff, which is much harder to do with the proprietary, uh, the vendor tools. Okay. So yeah, I add my state registers. If reset states st0, else state next. Always at yeah, no, definitely. I mean, that's why I usually prefer instantiation to trying to infer anything. And some of the blocks that I implemented are definitely more instances. Like the way I started working with FPGA was implementing digital cinema stuff, and we were trying to basically beat the competition in area and everything, and fitting on the smallest possible FPGA. And there was so many manually instantiated, like LUTs4 and stuff like that, optimized, like hand optimized with sometimes hand placement and stuff like that, just to get the absolute most that we could of the FPGA. So flush is going to be if fr empty state next equal st0. So yeah, control active. So if we if the host tells us to go active, we go active. And if the host tells us to shut down, we flush and then we shut down. That's pretty much it. So no, I think we just need to implement the Wishbone interface. So it's a fairly simple interface. Why do you redesign assign zero? State next was a reg because anything that's assigned in a always block needs to be a reg. That doesn't mean it's a register. I mean, it's a Verilog register, but it's not a flip-flop, right? But anything assigned in an always block needs to be a reg. And if it's in a clocked process, I will use this, which is the non-blocking assignment, I think. Yeah. And if it's in a combinatorial block, which is always at star, then I assign them just with equal, which is the other one, the non-blocking assignment. Yeah, that's one of those Verilog foot guns. If you don't do that, you have weird synthesis results and possibly latches, and then generally crap happening. Yeah. I mean, don't get me wrong, like Verilog is definitely not perfect and there's plenty of things wrong with it, but I so far haven't found an alternative that fixes the real problems that I have with it, which is having the tools actually implement what I want to implement. Yeah, oh, definitely. If I started with VHDL, right, and I much prefer VHDL and stuff like that. I will say that there's a lot of stuff in Verilog that I'm not using here. Like you have always FF and always comb and that kind of stuff, which are much better and remove the like system Verilog constructs. Same thing for when wiring buses and stuff like that. Like I do them signals by signals, but in system Verilog you can define buses and mod ports and that kind of stuff, which are much nicer and stuff like that. Unfortunately, if I limit myself to the subset of Verilog that's supported by Yosys, iVerilog, and very later, well, I'm pretty much stuck with basically just Verilog and very not a whole lot of system Verilog, basically. So that's the one thing I regret about the open source tools is that if they all add complete system Verilog support, that would be great, but they don't. So yeah, so where was I here? So all Wishbone access take 2 cycles. That's just the way I usually code my interface when they don't need anything particular. I'm gonna prefix that with B for bus. I don't really want to use WB prefix because the WB prefix is used for the external interface. So no, BAC. So I want to write enable to CSR, and then I want, you know what? I'm actually gonna have a registered write enable. Yeah, Ed, I'm still going, and that's definitely lasting way longer than I thought it would. I haven't even started on the HDL, on the software part, which is really what I wanted to show is the USB part, because the hardware is taking so much longer than I thought it would. I talk too much, I think. But hopefully the hardware should be at least very soon in a state where we can simulate it very quickly to verify that it does something sensible. Well, thank you. I hope at least it's interesting, and it can be useful, and hopefully that I can also point at how people can reuse the core and use the build system and example and cores that I put out there, so to integrate in your own project, either reusing the submodules or even just copying the code. There's a bunch of HDL code that I implemented here that if you want to re-implement them yourself, for learning processes, by all means go ahead. But sometimes you just want something that works, take it and use it, and yeah. So here I'm basically doing a bunch of signal that are gonna be my write enables for the various registers that I have, which are the volume, FIFO, and the control registers. Wait, how? Just trying to remember how I did. I mean, I can sometimes take an example of how I implemented the registers and yeah, I use the ACK as the reason basically. Yeah, I can do that. Okay. So what I'm trying to do here basically is have all those registers take one LUT, and so and so I know that it's going to take 3 ADDR to be, each one of these has 4 inputs, like 1, 2, and then the 2 address. So that's 1 LUT4 plus the register, and I'm using the BAC as a reset signal for the register. So that should all just take one. Which honestly, I mean, like it's 3 registers. It wouldn't really cost a whole lot or that kind of stuff. But I just try to generally keep in mind how much things are gonna take. There you go. These are my right strobes. I need to actually implement the actual registers though. So wait, this is gone. Our data is gonna be a register. So I have the volume. Where am I? Okay, here. So the first register is the control register. I only have one control bit, which is if I'm active or not. So that's pretty easy. I want a reset for it. Let's assign it to bit 0, basically. The next one is the volume. What the hell did I do? Start volume at 0 so that it doesn't generate anything while we're not initialized. And then the rest is the FIFO writes. So something to note here is if you attempt to write to a full FIFO, it will drop the samples. Like I could make it block the bus, but that's kind of dangerous because it will block the bus indefinitely. Like if you're not running and you write, like imagine the core is off, it's not reading data of the FIFO, and you write too much data to the FIFO, you could hang the entire Wishbone bus. Given that we have we will shortly have a way to check the status of the FIFO if it's full or not, I will rely on the software to do its job and not try to write to a full FIFO because I don't want to risk hanging the bus. Yeah, I haven't tried GHDL yet, but it might be an option now. It just given now I've started all my cores and stuff in Verilog, it's kind of hard to switch basically. What I have to check is if the cross support or is that and most importantly, even if synthesis with mix of VHDL and Verilog works, the simulation with cross VHDL and Verilog works, because that's also important. I want to be able to simulate all my stuff. Okay, so that's the acknowledge side, that's the write strobes, and then I'm using the write strobe to implement my control registers, and then here I implement the write to the FIFO for the data. And so here the only thing I need to implement is the read side, and if so the oh yeah, something I forgot is I need a counter that counts the number of ticks per USB frame. Which means I actually need to know when the USB frame happened. I'm gonna call that tick per frame. So what I'm going to do is actually have a continuous counter that increments at every tick, and then a register that captures it at every USB frame, basically. That's not where I need it. What the? I don't know. The indent is not working correctly on this machine. I don't. That's aggravating. Okay. So I will use the 16. Something I'm gonna do is USB audio. It's a kind of document the register map that I'm making for this core, because that's gonna be. Yes, I'm using an asynchronous reset through the clock. It's uh, it's only because it's on the iCE40. It's because on the iCE40 the reset signal is conditional to the clock enable, and so if I'm using a clock enable on the same registers, Yosis would have to combine both to generate the final clock enable, which is just annoying. But the asynchronous reset is not subject to the same condition. So I tend to use asynchronous resets on iCE40 because it makes the synthesis work better. Yeah, another one of those. Oh yeah, the architecture is weird, and you need to adapt your HDL style to that. So volume. So volume. It's a write-only register, and so 3116 volume channel 1. Honestly, I have no idea which one is going to be left and which one is going to be right, because I didn't pay attention to which pin is connected to what on the P mode. So uh, uh, No, I'm not using it consistently. I know. It's because I tend to use it mostly on signals where I don't care too much, because like it just resets it to 0. Like mostly it's for simulation, right? Because if that counter doesn't start at 0, it wouldn't matter much. But on something like the state register, actually this one I could put it something like the state registers, like it's absolutely critical that it works, and so I want kind of the timing to be analyzed and that kind of stuff to make sure that it resets properly. And so I will tend to use synchronous resets. Yeah, it also depends on the size of the register, because for 1 bits, I mean, honestly, I don't really even want to use the reset signal of the flip flops. So it's kind of, yeah, it's more a heuristic than an exact science, I would say. And also, I would say I'm not paying full attention to what I'm writing at here, because I'm trying to go fast, and so sometimes I forget some things. So where was I? Yeah. So these are the 16 bits. Then I want the FIFO level. The FIFO level is 10 bit, if I remember correctly. Yes, it's 10 bits. But what I'm gonna do is align it on 12 bits so that I can make a larger FIFO if I want to later on. And then here I have 2 unused bits, which I can later use for mute control if I want to. And then I have the running status. And the run status. Okay, so I have something, add something named control active, which I'm gonna rename to run. And running is kind of the status. So run is the command from the host. Does it want to run? And running is it actually running at the moment? And this is gonna be this signal. And so here I'm actually gonna use that running. Put that at the right place. Okay, I think so. The only thing I'm missing here is WA data needs to be. So I'm kind of using a slight variant of Wishbone. Is that if the peripheral isn't accessed, it needs to output 0 on read data, so that the read data of all the peripherals, when they're sent to the CPU, instead of having a mux, you can just OR all of them, which is much less costly in logic. And most of the time, because you have a read register for the mux inside the peripheral, the reset is kind of free. So the PMOD I'm using is the 1-bit squared audio PMOD game PMOD thing. I'm not sure if it's in the store already or not. Yeah, it is. This thing. That has a audio output, like here. That's what I'm using. It will not need a driver on the host side. It will appear as a standard USB sound card, USB device class. It will work natively with everything. To what do you add that audio capability? There seems to be already RGB UART. Well, here I'm just doing. I'm just adding the audio to base sock. It will only do audio. I've removed code that does everything else. Well, I mean, if you imagine how do you implement a mux in LUTs, it's much like if you want to implement a mux2, like in a LUT4, you can implement a mux2, right? You have the two input signals and then the selection signal, and then the fourth input is kind of lost because you can't do anything with it. And so in one LUT4, you can implement a mux2. But on the other hand, in one LUT4, you can OR 4 signals, right? And on some architecture, like not on the iCE40, but on the Xilinx, for instance, you can actually implement super wide OR using the carry logic. Like the carry logic is flexible enough that you can use it as a chain to implement super wide OR signal in one single layer of logic. I mean, single layer plus the carry logic, but which is really nice. Not bus cycle or I think that's correct. I'm not entirely sure. Oh. Yeah, no, I could just put 0 instead of 32H00. I just like the way it looks. Yeah, no, of course, you have to always count the carry logic impacts your frequency. But if you have the choice between the carry logic and OR3, an OR3 of several layers of LUTs, the carry logic is going to be faster. I mean, chances are. Honestly, I'm not entirely sure about that logic. Wait, I need. So I have the cycle signal, I have the ACK signal that I'm generating. 1, 2, so that's 1 clock cycle. So bus access looks like that always, pretty much. And so what I have here is not B cycle or not B ACK. So that so yeah, that's completely wrong. What am I basically what I want is a reset signal which looks like that. It's at 1 everywhere except here. Yeah, it can't be registered. Not B cycle. BRD reset. Yeah, I was originally trying to make it a register, but I can't make it a register. I need to it needs to react directly. And so yeah, if I'm not selected, I want to reset. And if I'm acknowledging, oh wait, no. Yeah, if the ACK is high, then I want to reset. So yeah, that's correct. Yeah. Yeah, thanks for double checking. I should have copied. Yeah, I usually have a template with the way I usually write these bus interfaces, and I didn't think of copying it here. I should have done that. Would have been faster. Anyway, I think we have everything. We have the bus interface that allows us to write the volume, allows us to write to the FIFO, and allows us to turn the thing running on and off. We have the states machine that will properly flush the FIFO. We have a tick counter that goes once every 500 cycles, which at 24 megahertz is going to be 48,000 kilohertz. No, 48 kilohertz, 48,000 hertz. We have the thing that counts the number of ticks that happen per USB frame and captures it. We have a FIFO that contains 512 samples, which should be more than 10 milliseconds of output. We have a counter that counts how many samples we have in that FIFO. We have the data processing that reads once per tick from that FIFO feeds it to the hardware multiplier, multiplies by the volume, and then takes shift the results by 14 bits, and then inverts the MSB to convert signed to unsigned centered. And then we have something that takes that and outputs it to the audio bits. So the only thing we are missing at the moment is I had to add, I need a signal every time there is a USB starter frame, which is something I didn't wire in the top level at the beginning. So I need to, well, wire it now. Where's the audio peripheral? Yeah, here. Now, obviously, that is going to need to come from the USB core. Okay, so that's if we look at the source code for the USB core, cores NO2 USB, RTL, USB.V. This has actually an output which goes up every time there is a startup frame which is detected. It's currently not wired. It was currently not wired, but I can just add it. Now there is a small issue is that this is in the 48 megahertz clock domain, so I can't just wire it. What's the ticks per USB frame again? Yeah, it's because because the USB clock is like the clock of the bitsy isn't gonna be perfectly synchronized with the clock of the PC, right? Which means that nominally I should output 48 samples per USB frame, but in practice it's going to be sometimes 47, sometimes 49. And to keep the FIFO levels synchronized, I need to feed back to the host how many samples I consumed in the last frame, basically. So yeah, the startup frame signal that USB core provides me is in the 48 megahertz clock domain. So I need to send that pulse across clock domain. And obviously, that's a problem I've had numerous times before. So I have a core which already exists, which sends a strobe signal from one clock domain to another with some limitation. It says here the strobe interval has to be, so it has to be like very infrequent strobe compared to the clock difference, right? But here we have one pulse every millisecond, which means it's very infrequent, and I can use that core. And the advantage of that core is that it's very small, basically. That's pretty much it. Okay, I think we can try to build that. So what I'm gonna do is just make sim, which will start the not do the simulation, but just compile the simulation, because obviously I'm gonna have syntax errors. So line 51, okay. Yeah. Mm. Okay, so it built. No warning, no errors. Something else I need to change in the makefile is to actually turn on DSP inference. So I need some. I need to override the default uses args. I'm gonna do that here. Because it doesn't matter for the simulation, but obviously it's necessary for yeah, for building. Sorry, I brain turned off for a second. So okay, I want to simulate this. Just quickly try to write a couple of registers, write something to the FIFO, and see how things are gonna work. I'm not like booting the firmware takes forever in simulation. Because anyway, I can't do it in that simulation because I don't have a simulation model for the I don't have a simulation model that I can distribute in the repo for the hardware SPI IP. So what I'm gonna do is I'm gonna modify the boot. I'm just directly in a modify the boot script, and use that for simulation basically. Okay, so that's here. So let me. So if you look in the firmware, there's something called boot.s, and that's what's executed by the firmware on boot. That's what in the first kilobyte of memory, and that's the only thing that initializes. And by default, the only thing it does is it can configure the UART to debug stuff because it's useful to be able to debug things. Sorry, I need to drink. But mostly what it does is initialize the SPI core and then read a certain amount of memory and copies it from the flash address to this address in memory, and then jump to it basically. What I'm gonna do is I'm just gonna change this to access or audio core and just do a couple of test stuff on it. So I'm gonna set the volume first. So let's say I want to say one channel at one is at full volume, the other is at quarter volume. I want the base address of the core. So the base address of the core is going to be, if you look in the hardware, the way this example and pretty much all the SoC I do are organized, you know, the Wishbone is separated. You have a 3, and audio is the 6 peripheral, and that means that it's going to start at address 086 basically. That's where it's mapped in memory. All of that from there up until 8600 FFFFF, all that address space is mapped to the 6th device on the Wishbone bus. Even though we only use like 4 address, but yeah. So, and we want to write that to the volume register, which is register 1. But register 1 is actually at address 4, right? Because it's 32-bit registers. So we want to store A1 to 4 A0. So we're going to load a few samples in there. 1, 2. A1. So that's register 8. 2, 2, 3, 4, 3. It's just random data. We're just not trying to play audio here. And then we want to read the FIFO level, which would be 3 at this point. And then we want to enable the core. And we want to write that at address 0. There we go. That should quickly test that we haven't screwed up anything, which is very unlikely that we haven't screwed up. Well, I mean, I haven't screwed up anything, but okay. Boot.x. Okay. I can run the simulation. So the thing is, the simulation will try to load the boot.x from the current directory, so I have to actually link it. It's not perfect, but I'll do the trick. Top tb.sim. So what did it complain about? Yeah, there's not enough. That doesn't matter. That doesn't matter. That doesn't matter. That doesn't matter. Okay. And we have our output. So the good thing is we see our Wishbone access here. We have a write of the volume, then the few data samples, and then here we have the read cycle. where is, and here we have the write enable. Okay, so far the bus access, it didn't crash the bus. The read data seems not impossible. Well, we'll have a better view when. So now we can at least check. But one thing that's weird is that the audio output here is XX, which is not a great sign. But I'm just gonna, now that I know that the top level of the SOC works, I'm just gonna remove those signals and just look at the signal inside the audio core that we implemented. Okay. So we did write to the FIFO write enable. We wrote our 3 samples, so that's good. Did the FIFO empty signal fell? So we have something in the FIFO, and we can see that the first data sample that we wrote has appeared on the output of the FIFO. So far, so good. Has the volume been set? We're not gonna see the volume because oh yeah, that's annoying. The thing is, iVerilog doesn't log arrays, so that's annoying. Oh well. Do we have the FIFO level somewhere? FIFO level 1, 2, 3. Good. So the FIFO level works. I mean, not really, because 3 is good. 202, not so much. 001, what? Okay, so FIFO level doesn't work. That's first problem. Let's look at that. So FIFO level, oh yeah, the FIFO level is 10 bits, which means that this needs to be 9. Yeah. Rerunning the simulation. Okay. Okay, now we have 3, 2, 1, 0. That's much better. Now, something I noticed directly is that we're consuming our samples way too fast. So there's an issue there, but we can actually look at that. Why are we consuming our so the tick logic isn't working, right? We have 3FF, 1F2, 3FF, 1F2. So I screwed up something in the tick counter. How did I write the tick counter? What's wrong with that? $10D498. Thank you. Okay, that's much better. We now have one tick every so often. I mean, they're not every 1 millisecond in the simulation, but honestly, I have no idea if I'm not sure my clock in the simulation is really 24 megahertz. So I would not trust that too much. But I mean, the timer starts at 1F2, which is 498, yeah, and decrement. So yeah, it should be one every 500. So my clock are probably not set up properly. Like if I look in 20.84, is that correct? What's the period for 1E9 divided by 24E6? 4166 divided by 2. Yeah, that's actually correct, more or less. So what did I screw up? 24 megahertz divided by 500. Oh yeah, but no, I'm an idiot. The pulse is not supposed to be 48. It's not supposed to be 1 millisecond. It's supposed to be yeah, like 20,933 nanoseconds, which is yeah, it's that. So okay, that's correct. So far, pretty good. Um, except we don't have any output audio, and the audio output is undefined. Except for that, works great. So why don't we have any audio? That's gonna be annoying. So I will temporarily modify the source code basically um, to have the signals as yeah. I mean that's not great, but at the moment I don't have any other idea. Okay, so now I should have yeah the debug signals here. Okay, so debug signals actually don't look bad. So that's pretty good, actually. Oh, and you know what? I can just look at the PDM cores actually. Okay, that's interesting. Is that the Oh, I think I know. I think the PDM core doesn't simulate correctly because one registers isn't initialized. Um, that's fine. Like I don't care what its reset value is; it's gonna work anytime. But in simulation, it makes it undefined. I should add a conditional reset in simulation or something. But I know the core works, so I'm fine with that. So I think the hardware is actually pretty good. No, the what I want to check is the read value. So when we read the status, did that work correctly? Um, so we had the bus access here, and we read the value. It was at the correct place, and FIFO level is correct. So the tick count, yeah, that works too. And this counter is correctly incremented every tick. Okay, so I think the hardware works. We can try to build it to synthesize it. Yeah, thank you for joining, Matthew. Yeah, I'm sorry, this is definitely getting a bit long, but yeah, I want to at least start on the USB part. I don't know if I'm gonna be finished, but yeah, I thought I had. Okay, didn't it take the right? Oh, I was in a okay. I was in another console when I said the export. Yeah, yeah, you're right. Yeah. So I wanted to actually check if the synthesis used DSP cores. It should have used two DSB Max 16, right? Met timing, no problem. What DSP? Two used. Yeah, okay. And we used 2800, so it's about 200, 250, maybe 300 LC, something between 250 and 300 LCs, which is, I mean, it's not bad. It's not especially optimized, but we have a bunch of counters and 32-bit registers and stuff like that. So that's uh, not terrible. Let's flash that. Okay. RPT search, I can try that, but RPT search rank. I don't see anything. Nope. Wait, I can actually look because I use Gain 2 on my main station. I mean, not on the streaming machine here, but no, it is not there yet either. Okay, so we have some hardware. Now we can get started on the software part. I will directly. I don't know if I don't know if we should directly move to USB part, or if we should try the hardware by trying to play like a sine or a constant note or something. Um, okay, thanks for the link. So can you actually paste it more like in Discord? Because I'm more likely to see it in Discord than in in the history of the of the chat here. Thanks. Okay. So now we're doing firmware stuff. The first thing I'm gonna do is, oh yeah, actually no. I just flashed the firmware with wrong boot code because I modified boot.s, right? And of course I can't do git checkout because it's not in git. I just copied it. Damn it. RISC-V USB firmware boot.s make boot.x. Yeah. Git restore. No, I still use git checkout. There's a git restore. Yeah, I don't get updated very often in new commands. There's a git restore. What does that do? Git restore is not a git command. Okay. dfu util -e. Okay, it boots. Now we can actually do some firmware work. So I should oh, okay. Yeah. I mean, I should split stuff in different files, but for the ease of doing it here and experimenting, I'm just gonna put everything in the main file and split it later. um, so the first thing I need to do is declare basically a variable where it's like the memory space of the SoC in case you reassign stuff so that you don't have too many hard-coded address. And so I'm going to use audio base for that. Next step I'm going to do is define a struct for that. Struct audio. Now, something you may have noticed in the Wishbone logic that I implemented, I only support 32-bit wide access. Like most of the fun, I don't bother supporting. I mean, read of a byte and anything less than one word works because that's handled by the CPU itself. It just issues a 32-bit access and selects the part that it wants. But byte write or 16-bit write are not supported. So you always need to write 32 bits at a time. Makes the logic easier. And I mean, here I really only want to write samples at once anyway. So I can't push in the FIFO just the audio, just the left audio channel. That doesn't work. There we go. So it's yeah, I'm not on the latest. I'm not on the latest Ubuntu, so I probably don't have the latest Git on this. Yeah, I'm 220, so yeah, it's definitely not very. It's not the latest Ubuntu. I haven't bothered updating this machine yet, basically. Mostly because I'm almost my root partition is almost entirely used, and so I'm afraid that if I try to update, it's gonna crash in the middle and leave me with an unbootable system. And I don't want to risk that at the moment. So I just want to try to push a sign. Not, I mean, I'm not gonna bother with a sign. I'm just gonna do something like some audio so that I can check that it works. How am I gonna do that? Okay. So this SOC in particular doesn't have an interrupt, because most of the time in here and in the project that I've implemented, I really don't have anything to do in the main code anyway. So it's not like in a microcontroller we can, shut it down to save power or anything like that. Here I don't really have any power management features on that SOC, so whether or not it's running doesn't really matter. And so instead I just have one main loop that just poll all the devices permanently, and that saves me the interrupt logic and the overhead of switching context and stuff like that. And so I just add a function audio poll in my main loop, which is gonna look at the FIFO level and try to fill it until I have, let's say, 200 samples or something. So just to explain what I'm doing here, if it's not clear, I'm just doing like the quickest hack I can possible to output like some form of audio. Doesn't matter the frequency, doesn't matter anything. I just want some audio. So I'm just also gonna set the volume, audio volume equal 0x 20000. Actually, I'm gonna make one half of the other, or 1/4 of the other. Yeah, I think I'm gonna. Yeah, I think I'm gonna do a sawtooth. Basically, it's just basically increment of one value and just set it over and over. FIFO, no, audio regs. Actually, here it was audio regs. FIFO equal V or V shifted by 16. So I'm resetting and rewriting the audio regs at every iteration, but that really doesn't matter, right? And audio FIFO level. Yeah. Indeed. Again, nice catch. What? Oh, I haven't included. Okay. Yeah, yeah. Wasn't D? Oh no, D is USB disconnect. Damn it. Just disconnected USB. Yeah. Okay. C connect. Okay. And then P. I mean, the state is correct. We ask it to run and it's running. The FIFO level pretty much stay at 200, which makes sense given that we're keeping it at 200, and the audio tick is changing. Obviously, it's way too fast to follow it by sound. So now the question is, do we have audio? So I did actually prepare something. Okay, so I have absolutely okay. It's muted because I have absolutely no idea of what audio level this is gonna be. Um, Wait, maybe I should actually, because I'm not gonna hear it if I plug it there. Okay, let me first try to check myself if I can hear anything. And then I will plug the audio. Try to pipe that audio. Yeah, you can't hear anything. You just hear one tick, like from time to time. Actually, let me try to pipe that and see if you can. I'm not sure if it's hearable. Can you hear that? Uh, can you hear my voice? Okay, I have no idea because I tried to enable. Okay, I tried to add a second channel, but for some reason it seems to be my mic. Wait, but what? How is that possible? Okay, so this apparently just ended up being another copy of my mic. Even though it's configured to be. Yeah, I think that's gonna what I'm gonna have to do because I don't. But I mean, here you're not gonna hear anything because you don't, because I don't hear anything. The only thing I hear is a very small tick tick from. Yeah, it's barely hearable. And I think that's what Conrad is saying, is because it's way too slow. And so the only thing we hear is the sawtooth basically. So I need to speed that up. Um, I think the microphone is very directional. Yeah, but yeah, you basically hear a very weird sound. But it's kind of weird that I can't pipe the audio. Yeah, it sounds horrible basically. But the most important point is there is actual sound. So now we can move on to the next phase, which is actually implementing USB, which is, oh man, I thought I'd be starting this way earlier. I probably won't be finished today, but I want to at least show basics of setting things up. So I'm gonna shut that down because that's make a horrible sound. So we want the device to appear as a USB sound card, which means that we need descriptor that identify it as a USB sound card. If we go to the documentation, so let me close this. That's the kind of descriptor that we want. We want device descriptor, configuration descriptors, all those are standard. And then we need an audio control interface, which is basically the way the host sets the volumes and that kind of stuff. And then we need, and that's also the interface where the sound card is kind of described, what it contains. And then we're gonna need interfaces for the data flow, and that data flow interface is gonna have to have alternate settings, so two different configuration, if you will, because that's just the way isochronous interface works in USB. Is that because isochronous interface reserve some USB bandwidth, you have to have a way to turn them off. And so usually you have an alternate setting 0, which is the default, which is has no endpoint and has no data flowing through it. And then when the host actually wants to flow data, it configures the interface and then to go to the alternate settings 1. Basically, it's another operating mode, and that one will have some reserved bandwidth, some endpoint, and that kind of stuff. We won't have an HID endpoint here. So this is just an example from Silicon Labs, right? And so we're gonna look at the descriptors now. So the descriptors in actually I can go here rather. I've put them in a separate file. You have the string descriptors that are in the text file. So you have string 1. It starts as string 1. String 0 is special. Here the string 1 is always the serial number. It's initialized to 0, and it's actually initialized to the flash unique ID on boot. But I need to reserve some space for it. That's why it's set to a bunch of 0 here. And then you have the vendor string, the product string, and then the configuration and some other strings, which the three first one are pretty much always fixed and always the same. The rest is going to be dependent on the actual descriptors you have. So if you look at the descriptors, the way I've implemented them is basically using C structure, right? That represent the various structure that you find in the USB descriptors, and then you initialize them as a initialized C structure. And so that's what we're gonna have to do for USB audio. So currently, I mean, as you see in the message, it currently initialized as a CDC device. That's because I have a CDC interface set up. I'm gonna remove that because we're not gonna use that at all. And then we have the DFU runtime interface, which is what allows the device to be listed here, and reset to bootloader, and we're gonna keep that, and we're gonna actually set it to the first interface. Then we want an audio control interface. Well, actually, we're just gonna. I'm just thinking. Oh, I'm gonna organize this thing. And the first thing I'm gonna do is actually take a new console and cores USB. So I've already kind of made the structure for USB audio class, and so they're defined here already. So I can already set them to their proper value. I just need to do a bit of cut and pasting, basically. So as I said, we're gonna need an audio control interface and an audio streaming interface. I can remove the CDC stuff and the interface here for 5. So here, every time you have like E interface, E is an index of the string, and so you have the name of the configuration here is stored in string number 4. Here, the name of this interface is stored in string number 5, and so once you edit this, you kind of need to match the string here, which is string 1, 2, 3, 4, and so string 5 is going to be the FU runtime. Yeah, which is not ideal, but unfortunately, you can't just I couldn't easily just make a string here, basically, because that's compiled, and yeah, in C++ with construct or something like that, I could have done that, but here you have to manage your string separately. Okay, so we want an audio control interface. So I'm basically copying the example because I had no idea how to. And so an audio control interface, you have the standard header and then some specific headers for it. So that's gonna start with the standard interface descriptor. And then we're gonna need damn it. Sorry, I'm getting lost in the interface header audio class descriptor. So it's gonna be this thing. Now, not everything can easily be represented by structure, because here you see that one of the field is a variable length, which means I can't just include it in the structure. I have to manually add it, which is not great, but yeah. Unfortunately, that's the way it is. And then I have an input terminal, a feature, and an output terminal. So just to quickly explain the way USB audio works is you're basically trying to describe. Wait, that's not this. It's this one that I wanted to show. You kind of need to describe the flow of data and the switches and all the functions that are available in your sound card, because I mean, it's nice in the sense that that allows an application that knows nothing about your device to expose meaningful controls automatically just by passing the descriptor and that kind of stuff. Unfortunately, because the there can be a lot of different devices with a lot of different things doing different stuff. That means that this description is not particularly trivial to write. It has to be quite generic, and I mean, true. I mean, it's full of those kind of weird things. But on the other hand, I'm not sure I would have come up with a better way of doing it, basically. But yeah. Here, however, our sound card is the one we're implementing is very easy. I think there is a model which matched pretty well at the beginning. What we're trying to describe is, come on. There was a few examples somewhere. Well, actually, wait, I can't find it. What the hell? I thought it was at the very beginning. I mean, anyway, we so you have you're describing flow of data, right? And so you have input terminals, output terminals, which are things that produce data and things that consume data, and then you have like feature units, which are units that do stuff. And so you can have something here like feature unit, which define volume, mute, delay, bass boost. You can have some selector unit, which are represent selecting one option or another, mixer unit that combines different things, that kind of stuff. Here we will just have yeah, sure. We will just have an input terminal which is of the type USB streaming, so that's basically a USB isochronous endpoint. We will have a feature unit which will only have the feature of volume and muting, nothing of the other possible feature. And then we will have an output terminal, which is analog headphone output, basically. That's what we need to describe. And so we need 3 descriptors for that. After the header, we need an input endpoint descriptor, which is this. We need we're gonna need an output endpoint descriptor. And we're gonna need a feature descriptor here. And yes, you can see this has a variable length field, which means I need I honestly have no idea how long it's gonna be yet. Okay, so that's what we're gonna need for the audio control interface. Yeah, I wish there was like there was some old USB project, some old Python project which had like a graphical editor for descriptor, which I thought would be a good idea, but unfortunately it's been abandoned for like 10 years and it doesn't support a lot of things, which is unfortunate. But making they are so flexible that making like something complete is very, very hard. I can imagine. So the next thing we need is the audio streaming descriptor. The audio streaming interface. So we need a standard interface descriptors. We actually need two of them because of the alternate settings. One with nothing and one with, well, something. So one that doesn't reserve any bandwidth and one which actually reserve stuffs. And if we look at the example, what else are we gonna need? So we're gonna need some stuff that describes the formats. So the audio stream, audio class descriptor, the format descriptor, and then the endpoints, and then information about the endpoints. Okay. Um, so that's this thing. So that's this. Then we have the format descriptor, which is the one just below. So there's actually several possible format type. We only support format type 1. That's the only one I transcribed. That's because format, you can describe the fact that you accept, MPEG audio directly compressed, or AC3 or DTS and that kind of stuff. Here I just support the type 1 format, which is basically PCM, and that kind of stuff. Hey, welcome back. We started implementing USB, so yeah. And of course, this thing has variable length field. I think it's gonna be 3. Yeah, we finished implementing hardware and doing some very basic validation. And yeah, oh, thank you for summarizing. What else am I going to need here? I need the endpoint struct USB endpoint descriptor endpoint data, and then I also have the feedback endpoint. And for the end, I think isochronous, yeah, the audio class has a special endpoint descriptor, which is, yeah, this thing. Okay. So that's basically the structure we need to fill. And yeah, all the structure we need to fill, which is gonna be fun. Let's fill them. So these are the standard header for an interface. So I can just copy most of them. I'm gonna set all the string to 0, which is no information for now, because that's just gonna be easier. Oh wait, this is interface. Interface numbering starts at 0, right? Yeah, interface numbering starts at 0. So this is gonna be interface number 1, alternate setting 0. Interface class is gonna be, did I define constant for that? I mean, the subclass is gonna be audio control. Protocol is gonna be 0, I guess. Interface class, USB proto. Did I didn't define a variable for that? I guess not. No, we dropped it. We didn't look at it further. Wanted to move on, basically, not start debugging users. So interface class USB is 0, 1. I apparently haven't defined a constant for that yet, so something yet to do. I can define the two interfaces here as well. Interface, so wait, dot interface 0, interface 1, okay. So these are not gonna be audio control, they're gonna be audio streaming. What did I call that? Audio streaming? Yeah, audio streaming. I mean, something else that would be fun to implement is actually the MIDI streaming, so that you can then just feed that to like a FM synthesizer core and implement a FM device, something. Audio streaming. So this is interface number 2, and alternate settings 1, and we have 2 endpoints. Okay. So at the moment, I'm not entirely sure what I need to fill in those fields. So I'm just gonna prepare the template and then look at what I actually need to fill and how I need to fill it. Sorry, it's not the most interesting content seeing me cut and paste stuff, but yeah. wiring up a bunch of descriptors. That's and USB audio is definitely not the simplest of the descriptors. Some of these fields that I remember when I read the doc, what they mean. Some of them, not so much. Mm-hmm. And the output endpoint. B descriptor type. Wow, yeah. Damn, someone is paying attention. Okay, so that's it for the control ones. Okay, I'm gonna do the other. I mean, I still need to fill in the value, right? But the boring cut and paste part is done. So endpoint data. Okay, so here there is another specific structure to this. General. Okay. I mean, some stack. If you look at like Lufa, for instance, like the other stack I know for AVR stuff like that, the descriptors are not. They're not USB struct. Like they didn't bother. They're just like a flat UNT8 array that you must create manually, which might be easier to cut and paste stuff like that. But I kind of like the fact to have them as actual structure that can manipulate, especially because the stack can then introspect some of the values more easily. I mean, does struct make you cry? Sorry. Do you have a better way of representing that? Ah, yeah, the flat. Yeah, yeah, exactly. Yeah. Yeah, that's the nice thing is then I can use size off and stuff like that a little more easily than manually updating some values and stuff like that. It's not perfect because it doesn't map entirely to C. I think in C++ with modern construct stuff like that, you could probably do something that's actually not too bad. But um, I am not a good C++ programmer. I don't know modern C++ basically. So API data is it's like the standard USB endpoint structure, which I don't have in this C file. So I'm just gonna look at this and then okay, finally getting there. So now I need to look in the USB proto.h. So in general, so that's the source code of the USB stack I implemented. You don't have to use it. Like I also have a tiny USB driver for my USB core, which you can use. Yeah. Yeah, I haven't actually seen like most of the streams I've seen from you were actually KiCad stream, and not so much programming streams. So I should look at those to see a good C++ code. But I know um, you know C++. I mean, from comments I've heard you say and talk about. So yeah, what I was saying. Here you have in the NO2 USB, you have the source code for the USB stack that I'm working on, which is by no means complete at all, but it has a basic stuff. But you don't have to use that. Like you can use my USB core with tiny USB if you want. I implemented a basic tiny USB driver for it, which is what's used in the Acade badge, and then you get like a more complete possibly USB stack, which was already support for like uh, media storage and that kind of stuff, or integration with other projects that already use tiny USB, that kind of stuff. Yeah, yeah. You need good hardware to run the software. And so in all the proto.h file here is basically all the structure used by all the defines, all the magic values and stuff like that used in the USB specs. And so if I look in USB proto, I will find all the stuff that's generic, including the endpoint descriptors. And oh yeah, actually, now that I remember, I shouldn't have used endpoint desk. It's actually endpoint a CC endpoint desk. So it seems that they realized that a lot of the classes needed a couple of more fields for the endpoint descriptors, and so they have like an extended version of that structure. Okay, we're almost done with the boring cut and paste part, and then we can actually fill all those values with meaningful things. And then we should actually be able to just load that, plug it in, and it should enumerate as a sound card. It would most likely throw some errors because I pretend to be a sound card and implement none of the logic for it, but it should at least enumerate. Okay, so now we just need to fill all that crap, right? So that's B length. It's always going to be the size of the structure itself. It's size of and not struct, but yeah. Descriptor type is USB class specific interface, class specific descriptor type interface. The descriptor subtype is this thing. Okay, the other fields, BCD, ADC. Okay, that's the version number. BCD is always a version number, and it's spec 0100. Total length. Okay, then that I have no idea what it is. W total length. W. Certain for a class specific audio interface includes the combined length of this descriptors and all the units and terminal descriptors. Okay. So it's the length of all this of all the extra stuff that I'm adding after the interface descriptor. So size of app desk appconfdesk.audioctl minus size of the number of audio streaming and MIDI streaming interface in the audio interface collection. So I only have one. And then here it's the interface number of the audio streaming interface, and the audio streaming interface is going to be audio streaming interface 2, because that's interface 1, the audio stream interface is interface 2. Length, size of, struct, this, descriptor type, CSDT interface, input terminal. I'm just gonna fill the easy field first. Size of, struct, descriptor type, descriptor subtype, feature unit, size of, struct, output terminal, descriptor type, class specific descriptor interface, output output terminal. Okay. So now we need to actually fill these things. Terminal ID. Wait, I need to switch so that you can see the spec and not just me. Input terminal descriptor. Terminal ID. Constant, uniquely identifying. So basically, yeah, every unit has a number, like, and so I'm just gonna call that 1, 2, 3. And then, I mean, the input doesn't have any input, obviously, but the feature has an input, and the source of the feature is terminal 1. And here, the source of the output is the output of the feature unit, which is unit 2. I terminal is each time it's the name of the, every time you have an I, it's a string. And so here I'm just going to set 0 because I don't want to name. At some point, it's nice to put some string that allows the user to identify and stuff like that. But at the moment, I'm just going to set them to 0, which means no string. Same thing for the channel names. You can override left and right and set some custom names if you want to. Here, I don't really care. W terminal type. So terminal type are in a different spec, and our input terminal is USB streaming, which is this value. ASOS terminal. Okay, that I have no idea what that is. ID of the output terminal, which the oh, you know, association is something that we don't. It's when you have a microphone and a headset that are, you know, kind of part of the same unit. You can kind of associate them logically, but here we don't care. We only have one thing, so we're not associated with anything. Number of logical output channel in the, so we have 2 because we have left and right. And the channel config is I have no idea of the format of channel config. Let's just look at the example here. What did they use for channel config? Left and right. Okay. Feature descriptor. Okay, apparently I can't find that. Mixer unit descriptor, selector unit descriptor, feature unit descriptor, lang, blah, 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 unit ID, yeah, all of that. Size in bytes of the, okay, so 2. Yeah, it's because they use a byte array basically, and I'm using a uint16, which is going to be mapped in Little Indian automatically. I mean, I don't do Indian conversion really. It's just that I assume that I'm running on Little Indian because there you go. Uh, okay, so control size is okay. So you have controls. You have a control 0, which is the master channel, and then you have a control for every logical channel. So I have 2 channels plus the master, which means I have 3 channel, and each of them is 2 byte because I want to be able to support all of these, which means that I need 6 byte for this array. BMA controls, where is it? And so for the master, I don't have a volume for master. I only have volume for left and right, and then I have I'll implement a so here I have mute plus volume, mute plus volume. So for the master channel, I only support mute, and then for left and right, I have independent volume. I don't know. Yeah, because I would say more like Intel, right? Intel is a big. Didn't Intel like design USB? Okay, yeah. Okay, and then E terminal. That's a string, which means I don't care about it. You can set it to 0. And so I need a terminal type for the output terminal. So terminal type, output terminal type. Well, it's a headphone jack. That's probably, yeah, let's go with headphone. And associated terminal, there's no associated terminal. Okay, size off. This descriptor type is gonna be this. Descriptor subtype is this. Terminal link. What does that mean? Oh yeah, okay. So basically here we need to tell him, okay, this streaming interface, which is like these USB endpoint, they correspond to this particular input or output terminal. And so here I named it terminal ID 1. So I need to say 1. delay and format tag. Introduced by the data interchannel synchronization. Yeah, so the spec kind of supports audio synchronization. It's used so that two different USB audio peripheral can so you have two USB sound cards, for instance, and that allows you to output sound synchronized on both of them by specifying which delay you have. And for here, since we're implementing the asynchronous model, we actually don't support that, which means that delay is meaningless, which means we can set it to 0. And W format. So I need the format. Format. PCM. Yeah, I mean the USB actually spec a bunch of stuff. I have no idea which device implement what, but yeah, there's definitely a bunch of features. Like you can declare a device can declare, sorry, how long, like how long the between the USB frame start and the moment it starts outputting that particular audio samples, and also how much USB frames it takes it to lock its internal clock reference to the USB frame rate and that kind of stuff. Format, B length, okay, size of struct USB AC AS. Format one desk. Descriptor type. Descriptor subtype. Format type. B format type, okay. Well, yeah, the number of channels, there's gonna be 2, right? Yeah, we have 2 channels. Subframe size, number of bytes occupied by one audio subframe. 1, 2, or 4. It's 2 because we have 16-bit samples, so 16-bit sample. As sample frequency type, we support not continuous, we support a number of discrete sampling frequency, we support 1. And that's only 48,000. Okay, we're getting there. Struct USB endpoint CC endpoint desk. That's actually the same as here. USB DT endpoint. USB class specific and descriptor type endpoint, and that's the name of the structure. Okay, that's all the easy fields filled in. I'm just gonna go quickly grab something to drink. Give me a second. Okay, so endpoint address. Endpoint one. I don't have any other endpoint, so I can start at 1. That's out 1 or 1 out. And here I'm gonna use 0x81. There's gonna be 1 in. Max packet size. So okay, we have 4 bytes per sample, 48 samples per frame. That's 192 bytes. But we must be able, because we're not synchronous, we sometimes must be able to receive more samples and sometimes less samples. So I'm gonna make a maximum packet size of 1.5 times the nominal size. So 192, 288. Perfect. Sounds about good. 288. Bit interval, that must be, wait, I'm gonna do the attributes first. What did they, oh yeah, that's not gonna help me much, I think. Okay. So we want it to be isochronous, so that's 0, 1. We want it to be a data endpoint, so that's 0, 0, so that's 0, 0, asynchronous, 0, 1, 0, 1, 0, 1, so that's 0, 0, 5. Data, isochronous, async, isoc. This is going to be 0x. This is going to be the feedback endpoint, which is 1, and then no synchronization and isochronous, so that's 1, 1. Feedback, isoc. Max packet size, I need to send 3 bytes, so 8 is good. Let's see if there is bit interval. Okay, must be set to 1, reset to 0. Okay, that's easy. Yeah, I mean interval is like every how many frames, and we want 1 every frame. Same thing for here. And sync address is the address of the endpoint used for feedback for that endpoint, which is 81. Oh wait, this rate must be. So I know that can be 0. But I can set it to 1 if he really wants to, but. Okay, and so that leaves this endpoint gen. Blah blah blah. BM attributes. Indicate control supported on this endpoint. You can't change the sampling frequency. It's fixed. You can't change the pitch. And we accept packets of any size. So 0. Lock delay units. Time definite will be lock in synchronization. We don't have any clock recovery, which means 0 0. Okay, that was easy. I think that's it. Of course, it doesn't build, but probably because I need to include the proper header for all those structures. Much better. 135. Another dot that they're confused with a comma. And it built. Okay, well. Let's program that and see what happens. Yeah, exactly. What I hope is that it's not going to crash the machine I'm streaming on, because that would be very annoying. I mean, if the stream stops, you know what happened, right? Oh yeah, I'm an idiot. It did something. Invalid UAC header v1. Oh well, that's helpful. Yeah. So I screwed up something somewhere. Really? What should I look up? Oh wait. Oh yeah. I didn't see that. Config what contains an expected descriptor of type 02. Okay. So oh yeah, you know what? Here it's the size of the struct, but I also need to add the size of the manual bytes that I add at the end, right? I think that's it. So let's retry. Well, it's nice that it eventually gave up. Yeah, I mean, that's not surprising, but there is no enumeration error. Yes. Yeah, I guess if it can't initialize it, it doesn't display it. LS, oh yeah, that's a good idea. LS USB dash V dash D1 Z50 6137. That's not the right idea. 1D50 61 47 46 46. What? Oh no, 6147. Okay, there you go. So interface descriptor, audio, yeah, audio control interface. Interface number 2, input terminal of USB streaming type with left front, right front. Yeah. Mute control, mute and volume control, mute and volume control. Yeah. Output terminal, headphones. Makes sense. Interface 2, alternate setting 0, audio streaming with no endpoint. Interface number 2, alternate setting 1, 2 endpoints. PCM, format type 1, 16 bits, 48 kilohertz sampling, 1 endpoint, isochronous, feedback, none, EP1 in, EP1 out. That looks good to me. At least I don't see any errors. Yeah, I think it's because I did it as a user and not as root. So it can only access a cached descriptor and not. Well, that doesn't help. Oh, it's probably because I don't respond to those requests, most likely. No, those are device qualifier and debug descriptors. They're other types of descriptors. Like you have the string descriptors, the configuration descriptors, stuff like that, and a device can have other type of descriptors, but that are not. They don't actually even exist in USB 1.1. The fact that I don't specify the strings are just. I mean, we can add strings. Like, let's see, every time we need a string. So I'm gonna edit the string file here and add them at the same time, basically. Right. So 1, 2. So here I'm at string 6. So string 6. Audio control. I mean, I can. Channel names. 7. So it is gonna. Since I have 2 channels, I need left ear, right ear. I have no idea to name. I don't know if left is first or I don't know if I don't know which one is left and which one is right. Honestly, I haven't checked. So you know what? There you go. That's the channel names. Yeah, left front might be listed first, but honestly, I have no idea if I wired left and right correctly for the pins, right? So that's something we'll need to test. E-terminal. Okay. PMOD jack. 7, 8. That was string 9. Oh no, actually that's USB stream, and then this is 10. Bitsy audio stream off. And that's it. I mean, you don't have to assign strings, right? It's just because some of these names, like, why do you care if you name the interface? Like, it's not probably not displayed anywhere, but yeah. If we check the LS USB now. Wait, did I? I didn't save the this. And yeah, here we now have names: Bitsy audio stream on, Bitsy audio stream PMOD jack. Yeah, it doesn't know that it's 2 different names, but yeah, the strings appear. Okay, I think I'm gonna stop here for now. I will continue later. Maybe tomorrow I'll maybe ask when people would like the rest, where we're gonna actually implement the control requests and then the actual audio streaming because yeah, it's like midnight here, and I've been streaming for 5 hours, so that's getting a little long already. Um, yeah, hopefully it won't be too long to get the rest up and running. Thank you everyone for joining, and I hope that was interesting, and I hope that you will join me for the next part. And yeah, usually I stream for like 2 hour, 2 hour and a half, and here it's like 5 hours. Um, I was a little long coding the hardware. I thought the hardware would be way faster than it was. But yeah. Yeah, I don't have to type. I can just talk. Anyway, I will stop the stream now, but I will be on Discord. So if you want to chat or if you have question or anything, feel free to ask there. And yeah, thank you, and bye. See you next time. I will announce on Twitter and Discord when the next stream will be. Have a good night.